Input 2 cannot point to both 5 and 7.
Watch the scene first. The math is built into the world, so the quantities can be seen before they are named. Up on the bank, Kit, the Shiba Inu, keeps a close eye on the currents of input-output rapids. Down in the water, Sedge, the river otter, has to navigate the shallows. Her safe passage relies on a strict physical law. Every path she takes must have one predictable destination. In mathematics, a function operates the exact same way. A function is a rule that assigns to each element of the domain, the input, exactly one element of the range, the output. To successfully navigate the complex obstacles ahead, Sedge has to trust this single destination rule. Here at the input bank, she faces an immediate dilemma. The stone path suddenly splits. Read the math on the stones. A relation pairs input 2 with distinct outputs 5 and 7. Can this be a function? A function gives each input exactly one output. This breaks the definition. No, the relation is not a function because one input has two outputs. Identifying a broken rule instantly disqualifies a mathematical relationship, just like a split path traps the otter. Moving down into the one current narrows, the riverbed reveals a coordinate graph beneath the water. The graph of y equals f of x includes the point 3, 8. What does that say? The x-coordinate is the input, the y-coordinate is the output, so f of 3 equals 8. The point says the function assigns output 8 to input 3. A plotted point on a graph is simply a visual record of one successful input-output pairing. As lighting shifts over the pool,
3, 8 means f of 3 equals 8.
Sedge investigates a deceptive layout on the riverbed graph. This graph contains shells plotted at 1, 2 and 1, 6, sharing vertical alignment. Both points use the same input, x equals 1, paired with two different outputs, which breaks the rule. It fails because x equals 1 would have two outputs, 2 and 6. Vertically stacked points on the graph are the exact same failure as a splitting river current. Both break the one-output rule. At the massive flat stone serving as a function map, we find an active rule. Function g is given by g of x equals x plus 4. Pause a moment. What graph point must belong to y equals g of x when x equals 2? We use the rule to find the output for input 2. Evaluating the function, g of 2 equals 2 plus 4 equals 6. Because the calculated output is 6, the ordered pair is 2, 6. The point 2, 6 must lie on the graph. Evaluating a function's rule always guarantees the correct single destination point on the graph. Pulling back, the fully resolved continuous path of input-output rapids comes into view. Sedge rests safely in the clear water, while Wren wades nearby. In this landscape, the animal's physical path aligns with the numbers and symbols on the bank. Every valid current guarantees exactly one destination for every starting point, linking the rule to a specific coordinate on the graph. The environment shows the relationship. The notation simply records it. Looking at this final landscape, which mark in the environment proves the mathematical relationship, and how does Sedge's physical action make it true?
Input 2 gives output 6. So 2, 6 lies on the graph.